Thank you. Um, I'm going to talk about some ongoing work I'm doing with Chris Moore, which we hope to publish soon. This is searching for a ring-down overtone in GW15 and 914. So first, some background on ring-down. So the ring-down is the endpoint of a binary black hole merger. And at the bottom of the slide, I've got this example waveform of such a merger. On the left, we see the end of the in spiral, and then this transitions into the ring down on the right. So this is when your two black holes have merged, and it's radiating gravitational waves as it reaches its final equilibrium state. We modeled a ring down as a sum of exponentially damped sinusoids, and in principle, there's infinitely many terms in that sum, not all with equal excitations. But for illustration here, I've just shown 3 terms. So we expect there to be a long-lived fundamental mode. And then we now expect at early times there to be these overtones, which are modes that decay quicker, but have larger initial amplitudes. And it's these overtones which we're focusing on, which we're looking for in the data. Just to say that the frequencies and damping times of these ring-down modes, they're completely determined by the remnant black hole mass and spin. And this is a consequence of the no-hair theorem. So in this expression, I've got these frequencies in each term, which are functions of the mass mf and spin chi-f. And these are complex frequencies. You can split them up into the real oscillation frequency, and the imaginary part is containing the damping time. So there have been previous analyses in searching for these ring-down overtones. In a 2019 paper, IC et al. Claimed to have found evidence for a ring-down overtone in 5914 data. And this corner plot on the right is taken from that paper. This corner plot is actually showing a few results with a few different overtones included in the model. What I want you to focus on is this kind of orange yellow contour. This is the results from a model where you include fundamental mode and 1 overtone. And the claim is you're getting a overtone amplitude, which is significantly away from 0. It was 3.6 sigma, I think. So this was evidence for finding 1 overtone in the data. However, this was revisited recently in a paper called Tester et al., where they actually found no evidence in favor of an overtone. And there was also a follow-up paper by IC and Farr, which failed to resolve this tension. They insist that the overtone is there. So all of these results were done in a particular framework, a time domain analysis framework, which I'll talk a bit more about on the next slide. But we now are going to apply our novel ring-down analysis method to search for an overtone, and we hope we can contribute to this ongoing discussion. So to illustrate the idea behind our method, firstly, ring-down models, because of their abrupt start time, they're fundamentally discontinuous, which means a time domain approach is kind of natural because you can apply these sharp cuts to the data. However, it has some drawbacks. When you do a time domain analysis, which is what the previous analyses were, you have to fix your ring down start time. And consequently, you also have to fix your sky position. Also, you cannot really make use of the same well-established frequency domain noise estimation and analysis frameworks. In gravitational wave data analysis, it's usually the frequency domain you use. So we want to try and do a frequency domain analysis, and we propose to model the pre-ring down signal as a flexible sum of sine Gaussian wavelets. We then truncate that sum at the ring down start time t0, and then continue with the usual ring down model after a time t0. So effectively, the idea is we're marginalizing out the pre-ring down signal. So the top panel here is showing our waveform polarizations for the two halves of the model. a flexible sum of wavelets here, and then the usual Ringdown model here. You can see the two halves of the model are not continuous. There's a discontinuity. We impose no continuity between the two halves of the model in order to keep the Ringdown inference independent from the rest of the signal, rest of the data. However, when you look at the waveform projection shown in gray on the top panel, it's very much continuous. And so this is basically a continuity that's learnt from the data. It's like a data-driven continuity condition. And then just on the bottom panel, we're showing the whitened waveform reconstruction along with the whitened data, and you can see it becomes completely continuous. So this is a simple illustration with like one wavelet and one Ringdown mode, but in principle, you can include many wavelets and many Ringdown modes in the same way. So now I'll move on to some results. And this slide is to address the issue of Ringdown start time. So although we can, as I mentioned, vary the Ringdown start time as a free parameter in our analysis, we find it more useful to use some particular choices of prior. And that's what's shown on the bottom panel. So in the Hanford frame, we use these priors for the Ringdown start time, basically. We have a series of narrow Gaussians, and we use these to explore the dependence of our results on the Ringdown start time, and also to make comparisons to previous analyses. But along with these Gaussians, we have this black curve. Now this is actually a posterior on the time of peak strain from a separate analysis. An IMR phenom PV2 waveform was used. And the idea here is, say we want to make a claim about whether there's an overtone at the time of peak strain. Well, if we use this as our prior, we are effectively marginalizing over our uncertainty on the Ringdown start time. So this is like our preferred run. Then just as a technical detail, we actually just do two analyses, one without an overtone and one with uniform start time priors, the posteriors of which are shown on the top panel, and then we reweight. But you can just think of this as using different priors. So first of all, we can get posteriors on the remnant black hole mass and spin. And I'm showing here results where we don't include an overtone and a result where we include one overtone. And each of these contours are from a different choice of the prior. So the colors match up to what's shown on the previous slide. We also show the IMR remnant mass and spin properties from a full in-spiral merger Ringdown analysis. And basically what you're seeing here is, for these choices of start time, the overtone helps you get results consistent with the IMR analysis. And you also see our kind of preferred prior lies somewhere in between these different Gaussians, which kind of is what you expect. So the final results, the main results, and I should say these are preliminary, are subject to details being ironed out. Basically what I'm showing here is the overtone amplitude posteriors. So I'll just break this down quickly. So on the top panel, we're showing that T-peak prior, just to help you relate back to what I've shown beforehand. These are results from all of our different Gaussian reweightings. And you can see this behavior where, as you go to later start times, you get lower amplitudes, which makes sense. If there's an overtone there, you expect it to decay. So at late times, as amplitude is decreased. This kind of highlights one difficulty of this analysis, which is, which start time should I use? In the previous time domain analyses, you fix the start time, but clearly, depending on the start time you use, you can get a different result, or at least a different significance on your result for the overtone amplitude. So then on the right, we kind of marginalize over this uncertainty with our preferred reweighting, our preferred prior. So this is like our preferred overtone amplitude posterior. And these are the 90% credible levels. I see my time's up, so just to quickly say, the final panel is the base factors comparing the evidence between the two analyses. Again, you see the same behavior where at late times you disfavor the model because you're including extra parameters which you don't need because the overtone has decayed. And we have the marginalized base factor here, which shows some evidence for an overtone. And I'll just leave my conclusion slides up. Thank you.
Thanks very much, Eliot. So we do have one question from the audience, from Aditya. Do you plan to incorporate effects of the BMS frames on overtones in your Ringdown framework? Their importance was discussed in a recent paper by Zertusche et al.
Was that BMS frame, did you say?
BMS is what it says in the question, yes.
I'm not completely sure on the details of that. Perhaps we can follow up on Slack afterwards. We at the minute just want to search for this as has been done in previous analyses, the ringdown overtone of the fundamental mode, and get weigh in on the argument that's ongoing, whether it's there or not. Yeah.
Okay, and I see there's a hand up from John, who is on the panel. So John, if you want to go ahead and just ask your question.
Thanks. I'm sorry, I can't type it in if I'm on the panel for some reason. I was encouraged to see that you were using wavelets to model the in-spiral and the pre-merger bit. And I was wondering, when you do the truncation of the wavelets that causes your discontinuity, you say you do everything in the frequency domain, the analysis is done in the frequency domain, so that discontinuity will only exist if you go up to infinitely high frequencies in the frequency domain. So what's the sampling rate that you're using, and do you think that that might have an effect? Because your actual model, if it's written in the frequency domain, is continuous at all points.
Yeah, interesting question. Yeah. So we are just using the usual 4 kilohertz sampling rate that comes, when you download the data. We're not resampling at the minute. But yeah, so I guess that relates to why it becomes perfectly smooth when you whiten, perhaps. We write our time domain model, we enforce no continuity, then we do the FFT in the likelihood. And I suppose, yeah, I'm just thinking that's why it becomes continuous, at least when when it's roughly continuous in the time domain. When you go to the frequency domain at our limited sampling rate, it becomes completely continuous. We haven't really thought about how going to super high sampling rates would affect anything, or just different sampling rates. But that's an interesting point, which I'll think about.
Thank you.
Yeah.
Okay, thanks very much, Eliot. I think we now have a short break programmed into the schedule. So it's a chance for everybody to go and quickly grab a coffee or a cup of tea and stretch your legs and get away from the screen for a few minutes. So we will come back and resume in 15 minutes time at 10 to 3. Thanks, everyone.